In this video, I want to have a look at how we can use integration to calculate the area of composite regions. So sometimes we'll be trying to find the area of a region that's bounded by more than one curve. If that's the case, sometimes we need to dissect the region into two or more regions before we can evaluate their integrals. So let's have a look at an example. In this example, we're asked to calculate the area of this blue shaded region here. So we've got two curves over here. We've got the parabola y equals x squared, and we've got the function y equals x minus 6 squared. So the problem here is that it's not just the area under one curve, it's the area under two separate curves. So what we're going to do is we're going to split this region straight down the middle here, and then we're going to evaluate two separate integrals. So we can find the area under this curve between this x value and this x value, and then we can find the area under this curve between these two x values. Our first issue though is that we need to calculate that x value. So that means that we need to find the x value of the point where those two curves intersect. To do that, we're going to solve these two equations simultaneously. So we have y equals x squared, and we have this one, we're going to expand that out. So we're going to have y equals x squared minus 12x plus 36. So let's call that equation 2, this one equation 1. Because they're both y equals, we're just going to substitute 1 into 2. So we'll have x squared equals x squared minus 12x plus 36. Now if we subtract x squared from both sides, we'll end up with 0 equals minus 12x plus 36. Add 12x to both sides. So we'd have 12x is equal to 36, and I've run out of room, but divide both sides by 12, and we'd end up with x equals 3. So that means they intersect when x is equal to 3. Now this parabola here, because it's x minus 6 squared, that means it's this same parabola but shifted 6 units to the right. So because this one had a x-intercept of 0, it's being shifted 6 units to the right, so we know that that's going to touch at 6. So that's going to give us our bounds for our two integrals. So our area is going to be two integrals added together. So we've got the integral between 0 and 3 underneath that first curve, so x squared, that's a 0, it looks kind of like a 6, dx, plus the integral from 3 to 6 of x minus 6 squared dx. So we can go through and evaluate those integrals. So we're going to have x cubed on 3 between 3 and 0 plus x minus 6 cubed over 3 between 6 and 3. And we can substitute in, so we'd have 3 squared over 3 minus 0 cubed over 3. That's a cubed, not a squared, plus, what are we going to have? 6 minus 6 cubed over 3 minus 3 minus 6 cubed over 3. So this whole bit is just 0 and this whole bit is just 0. And what we end up with when we evaluate that is 18 units squared for that total blue area. Another type of question we might have is finding the area between two different curves. So if we have one curve, like f of x, and it's always below a second curve, g of x, in a certain interval that we're finding our integral in, then the area between those two curves, the area of that region, can be found by subtracting. So what that means is, for example, if we had a parabola and we had a straight line, and say that we wanted to find the area of this region in between them. So in that region, this blue line, this blue function, is always below the red function. Not always over the whole graphs, but in our region between this point and this point, our blue curve is always under that red straight line. So if we call this one f of x, and we call this one g of x, then we could find the integral. If we say that this has an x value of a and this has an x value of b. Find the integral between a and b of g of x dx. So that would find us the total area beneath that red curve. And then we would subtract the integral between a and b of f of x dx. So it's going to subtract the little bit underneath here. So let's draw our axes in to make that a little bit clearer. So if we've got our, it's really not very straight, but if we've got our y-axis and our x-axis, that first integral is going to find this total area here. So everything underneath that red line and above the x-axis. The second integral is going to find what's underneath the blue curve, so that black bit there. So when we subtract them, we're going that whole trapezium minus this section, and it just leaves us with that green area there. So we don't have to do that as two separate integrals though, we can put it together. So we're going to go the integral from a to b of g of x minus f of x dx. So you're going to subtract one function from the other first and then integrate. Sometimes that makes it a little bit easier. So our example for this one asks us to calculate the area of the region enclosed by the line y equals 2x minus 1 and the curve y equals x minus 2 all squared. So the first thing we want to do is draw a diagram to get an idea of what that looks like. So if we draw in our axes, the line 2x minus 1, so it's going to have a y-intercept of minus 1, so down here, and a gradient of 2. So it's going to be coming up this direction. So that's y equals 2x minus 1. The curve y equals x minus 2 squared is going to be a parabola with a vertex at that point 2 there. So we're going to draw our parabola in there. So that's y equals x minus 2 all squared. And we're trying to find the area of this region in here. All right. So what we need to do first is we need to find these x points. So those x values. So we need to find the points of intersection and find out at what x values they happen. So to do that, we're going to solve those two equations simultaneously. So we've got y equals 2x minus 1. Let's call that equation 1. And we've got our second one, I'm going to expand. So we'd have x squared minus 4x plus 4. Let's call that equation 2. So we're going to sub 1 into 2. So we'd have 2x minus 1 equals x squared minus 4x plus 4. If we bring all of that to the right-hand side of the equation, we're going to have 0 equals x squared minus 6x plus 5. Then we want to factorize that. So we'd have to have 5 and 1. To make that a positive and that a negative, they both have to be negatives, which means we're either going to have x equals 5 and we're going to have x equals 1. So we don't actually care about the y values of our points of intersection, just the x ones. So that means that this point here has an x coordinate of 1 and this one here has an x coordinate of 5. So now we know that, we know the bounds for our integral. So we can get rid of all this. Now we need to know which one's on top and which one's on bottom. So within this region, that straight line is above the curve. So we're going to have the area is equal to the integral between 1 and 5, the numbers that we just found. And then we're going to have the straight line, so 2x minus 1, minus this one here, so x minus 2 squared dx. So doing that, we need to expand that whole thing out. So we're going to have the integral between 1 and 5, 2x minus 1. Now we need to expand this out, but also keep in mind that negative. So we're going to have minus x squared plus 4x minus 4 dx. And simplifying that, so 1 and 5 minus x squared, 2x plus 4x, so plus 6x, and minus 1 minus 4 gives us minus 5. So now we can actually integrate. So we're going to have minus x cubed over 3 plus 3x squared, so that's the 6x squared over 2, simplifies to that 3, minus 5x between 5 and 1. Substitute in, so we'll put our 5 in first, so we're going to have minus 5 cubed over 3, plus 3 times 5 squared, minus 5 times 5, minus, and we'll substitute in the 1. So we're going to have minus 1 cubed over 3, plus 3 times 1 squared, minus 5 times 1. And working out that whole thing will give us an answer of 32 over 3 units squared for that area between those two curves. Now this method also works even if part of that region or all of that region is below the x-axis, it'll still work out to give you the right answer. If you had a problem where one curve was under the other one for part of our region that we wanted, and then it crossed over and switched, so it was the other way around, you'd have to split it into two integrals. So for example, in this one, if we wanted to find that blue area, if this straight line was f of x and our parabola was g of x, for this section, because f of x is below g of x, we'd have the integral, that's a, b, and 0. Between a and b, we'd want g of x minus f of x dx. And then we'd have to add on between b and 0. Because they've switched around, we'd actually want f of x minus g of x dx for that one. So just being careful, we might have to split it into two if those curves do cross over in our region. All right, so that's having a look at areas of composite regions.